Oh, good evening. Welcome everybody to the July meeting, believe it or not, of Orange County Astronomers. I think this is our third or fourth meeting that we've had virtually. They've been going really well. Thank you very much, Raisa, for everything you've been doing to make these things really go well. And we've got a great program again tonight. Before we get into that, I noticed that there was a slide in the preview show that said that I was spearheading an effort to deal with dark sky issues, which is an area that I'm very interested in, but unfortunately, I don't have the time to be spearheading an effort. So I'm actually spearheading an effort to find somebody else who would be willing to spearhead an effort to deal with dark sky issues. So if you are at all interested, please do contact me or any other board member. I'd be delighted to hear from you. And there's an awful lot that really can be done in that area that would improve matters for everybody and not just astronomers. Another announcement I should make is, in case people have not figured it out, we are not having a Starbecue this year. Normally we would have that in July. Obviously, July is not a good month for the Starbecue for reasons we have no control over. And it doesn't look like August is likely to be any better. So we'll have to do that next year. And people just save your recipes and plan to really go overboard next year. That'd be really great. As a last thing, this is more on a sad note. There had been some emails going around regarding a longtime club member, Vital Bharatha, who has been very active with outreach and been an active astroimager for a long time. And we just got confirmation today. Jim Benet emailed me just shortly before the meeting to say that he did get confirmation that Vital unfortunately passed away on July 4th. So to all of his relatives and everything, we're really sorry. Without more ado though, we will turn this over to the next portion of our program. And I think that would be announcements. Am I correct? Okay, so take it away, our announcement crew, Doug Millar at Company.
All right, so to start with the announcements, we're going to start with a tour of the new website. So let me get that up and then we will, okay, so share. There we go. All right, so when you come onto the home page, this is the home page. You can see right up front there will be information on the next general meeting. Right now they're online, but even when these go back to in-person events, that will still be there. And if you click on View Meeting Info, you'll see that this takes us where it'll give all the information, including the Zoom link to access the meeting, or an information about who's speaking, etc. Again, there will be, this information will still be here when we come back to in-person events. All right, so now from back onto the home page, there are two ways to access the calendar. First will be obviously click on the calendar tab. The second way to access the calendar will be if you come down here, there will be upcoming events. So at first it'll show just the few upcoming events, like the next 3. But if you click on View More, that will as well take you to the calendar, where it will show you a month-by-month view of all the club activities. And then on the website, if you're scrolling down, we're back on the home page now. If you come down to the bottom, 2 things to point out. Well, 3 things. Obviously, donations, if you would like to donate to the club, any portion, you can do that here. Amazon Smile. Through the Amazon Smile program, if you register your account through Amazon Smile, you can, a small percentage of your each purchase you make on Amazon will come back to the club as a fundraiser. So you can click on that link and register your account through Amazon Smile, and put OCA as the organization you wish to support, and then the club will get a small percentage of each purchase you make at no additional cost to you. Last thing on the home page, if you click on that Astro Shop link, which I just sent, you can, it'll take you to the OCA store, where you can buy t-shirts, various sizes. You can see those here, hoodies, more t-shirts, and various other OCA merch. And then lastly, to get more information beyond a mailing list, if you click on the About tab and then come down to Special Interests, you will see mailing lists for each club that you can, or each special interest group that you can join. So just click on the icon and it will put you on a mailing list. This one, the bottom right, that's the OC Astronomers group, that's going to be a general mailing list for the entire club, where you can get be put on the mailing list for general information about the club. So now we will go to the rest of the slideshow, and then I will hand this over. I'm going to start this. All right. And then I'm going to turn this over to the other half of my crew. Are you guys there?
Yes, we are. Waiting for the next slideshow.
Can you see this?
Yeah,
slide?
we see your special interest.
Oh, okay.
We're waiting for the new members slideshow.
Oh, okay. Sorry for the confusion. So all star parties are put on hold until further notice, as well as some special interest group meetings, due to the current circumstances and being unable to meet in person. However, the OCA board meetings and the beginners classes are being held online. So those can, on the calendar where I showed earlier, you can get more information about joining those. All right. New members.
Yes, new members. Are you controlling the slideshow?
Yeah.
Can you go to the next slide or?
Yeah.
Okay. There you go. Mm-hmm.
Hello, my name is Paloma, and welcome new members. We hope you enjoy this amazing slideshow that we have all created for you.
So Kyle.
Sorry, Kyle, you're showing the web page. You need
Yeah,
to
we're not. Yeah, we're still seeing the Orange County Astronomers Special Interest Group page.
Does this work? Can you see the slideshow now?
There we go. Yes, perfect. That's Paloma. There you go.
Back up for a second.
There you go. Now it's there.
Here's the slide. I'm sorry, I thought I had moved. So you can see the 2 dates for these special interest group meetings. They're meeting online. And then here's the new members slide. And then
There you go. Okay.
here we go.
Hello, we are the Special Interest Youth Group. We sadly, since of the pandemic, the OCA meeting, what is it called again? OERL meeting and field trip will be canceled because of the pandemic.
Okay, then next slide.
And all outreach events will be canceled till further notice.
All right. Hi, everyone. So I'm Cecilia, and I'm the rep for OCA liaison to WAA. And so we want to congratulate again Mr. Bing Wok for being the recipient of this year's Blair Award, who was supposed to be given off in August 8th. But the pandemic is affecting all our choices and decisions. Therefore, we might be moving in September, maybe even fall time, later in the fall. So we'll give you more info for sure. I don't think it'll be coming next month. However, when it does happen, it'll be through Zoom, and he's going to have to get his medal in the mail. Please also, if you can see there, assisting your members, and as well as Facebook, we have that also. And I love, Reza, how you've been doing the whole social, Twitter, everything for OCA. Good job on that. So for WAA, I'm doing the Instagram, and we're coming up with a YouTube channel as well. And the website's already there for you guys to follow it up. And now the next person, Galileo. Ready? Next slide.
Hello. Hello, my name is Galileo, and today is going to be a winning Divis. Okay.
Are you guys doing this one or am I?
We can do it, but I think you were going to do it. So at this point, we have a ton of telescopes, as you can see, to loan out to all the new members. So welcome for that. Due to the pandemic, we don't want to get John exposed or any of the other people. So it'll be on hold till further notice. And people have called and asked, so what do we do now that we have, members, we don't have anything to do? And that's when it comes in this Saturday at 10 at night, because we can't actually go out to the stars and get together. We're going to do open meeting. So those members that haven't been able to actually see the stars, do that this Saturday with us.
So, anything that you would like published in the Serious Astronomer newsletter? This is the club newsletter that all members get in the mail every month. Please send them to that email address. Things that can be put in include articles, images, observations, club news, etc. ANZA site, members are discouraged from visiting the site during the pandemic. If you do go out to the ANZA site, please ensure that you are following all of the governor's orders at all times. And then here was the open spiral bar meeting that Cecilia mentioned earlier. And then on tonight's agenda, the What's Up will be done by the Garrett family. And then the main speaker, Anson Delacio from UC Riverside. And the topic is Cosmic Dawn, the birth of galaxies in our universe. And thank you for attending this meeting. Just to put that out there, next meeting will be on August 14th. And that's it for the announcements. So thank you, and I'll turn this back over to Reza.
Thank you very much, Kyle. It's now time for a WhatsApp presentation. John?
Hi. Oh, just a moment. Okay, I've got my screen. Sorry, talking while I'm figuring this out. All right, are you seeing the WhatsApp introduction screen? Thank you for having me here. And my daughter, Emma, actually, I'm her father, will be doing the What's Up. Emma keeps me sharp at times, and so I need her. And so she's in the other room, but has her own microphone tonight. Anyway, so we'll put together a little What's Up. Let's see. First thing, I had to borrow a photo from last year to use to illustrate where the big planets are right now, Jupiter and Saturn. This is a photo I took last year. You can see the Sagittarius area, and here's where Scorpius would be. And these objects in this picture last year are Jupiter and Saturn, but this year they've switched places, and this is about where they are. I draw the planets really big in my diagrams. That gives me a little wiggle room as to where exactly they are. But if you look toward Sagittarius, you'll see two bright objects, and those are the planets Jupiter and Saturn. And what you certainly won't see, but you can, these two are approaching opposition, which means they're going to be at their closest to Earth for the year. The only unfortunate side of that is that they're going to be low in the sky. So whenever you get these planets in opposition in summer, they're going to be low for the same reason the summer sun is high. And so they're not going to be the best view, but still they're going to look pretty good. They're going to be up there. They're going to be up there throughout the night. And so on the 14th, Jupiter is closest to us, and on the 20th, Saturn is closest to its closest moment. And then you might not know this, but the planet Pluto is also in that pair.
Dad, Pluto is not a planet, it's a dwarf planet. Come on, that's astronomy 101.
Yeah, okay, corrections by Emma. And I also made sure that I didn't mislead anyone on the scale here. But Pluto is right between those two. And what struck me as a little odd or unlikely is that I always thought Pluto was noted for its very inclined orbit relative to the other planets. And so I asked a friend with his software if he could explain what's going on there. And this is the orbital path of Pluto that it's been taking, slowly going to the left of your screen for over the years. And this is the orbital paths of Saturn and Jupiter. So it's kind of a coincidence that Pluto happens to be crossing the orbital paths of the other planets at this time. And so that's something that doesn't happen, what, how many years? I forget what Pluto's orbit is.
Dad, it's 248 years. Come on, that's solar system 101.
Okay, I've been coached on Solar System 101 and Pluto Planets 101. But anyway, you can relish in the knowledge that Pluto is very close. It's crossing the paths of the other planets. But more to the point for seeing it is that it's finally getting out of the Milky Way. So if you do hone in on Pluto, it'll be easier to guess which little dot of light is actually Pluto. In the morning sky, I've actually, in the last few days, have referred a number of friends out to at 4 o'clock in the morning to go out and look for the comet, and none of them found it. So I'm just going to start referring them to Venus instead. But Venus is very high and obvious in the morning sky. And so you can see that, and it's a good time if you like to get up early to start tracking Venus as its phase goes from a little less than half to half and then full again over in the next few months. But the main object that people are pretty excited about after the last two comet failures that have come around the sun and broken up or evaporated or whatever happens to them there, where we finally have what looks like a good comet for observing. And this was taken by a friend from my astronomy club. I thought he did a very nice picture the other day. I got up at 4 on yesterday and took this picture through my 3-inch refractor, which I'm starting to use for a lot of photos. The refractor actually gives you, when I have it stopped down to f5 focal ratio, it gives you a field of view that's in the ballpark of what you get from a pair of binoculars. And so I'm starting to get all pictures of objects with my little teleview refractor so that I can give people an idea of how big something is in binoculars. But it's showing up pretty well. And here it is about a half hour after sunrise through a 50 millimeter camera lens, which generally approximates the magnification that people perceive. And so I didn't see it as a naked eye object in the other morning, but it sure was a camera ready object. And the Sky and Telescope has been very generous in spreading around their illustrations of where this comet is. The comet Neowise is in the sky, and you can see this morning it would have been here in the northeast, and then the next couple days it's going to be about in the same position at which I was able to photograph it yesterday. So my recommendation is that if you do have a low horizon, an unhazed horizon, one that doesn't have many obstructions, you may want to try to get that comet, because quite honestly, you never know what's going to happen to a comet, though this one seems to be pretty well intact. And then for reasons I don't quite understand, on the 14th and the 15th, it's also going to become visible in the evening sky as well as the morning sky. I'm not quite sure how that works. You wouldn't know, Emma, would you?
Well, I'm assuming it's because of this, for the same reason that Mercury and Venus can appear in the morning or evening, but unfortunately, I'm not actually clear on that one.
Oh, okay. Anyway, so here's how the path it's going to take in the evening sky later throughout this month, and I'm really excited about this. I'd started putting together a few drawings to show how it's going to change over the next 3 weekends. The next 3 weekends I consider optimum time to get out in the desert or something like that and view, because this weekend the moon comes up, but it does come up after a few hours after the evening. Next weekend's going to be a dark sky weekend, perfect time to get out there, and the weekend after that it's going to be a generous crescent moon on the weekend. So again, if you wait for the moon to go down, you get a lot of dark sky viewing as well as good lunar observing. But if you're looking up in the northeast, you see, of course, some of our favorite constellations, the Big Bear and the Little Bear, and the tail of Draco the Dragon. And I always enjoy finding Draco by looking between the dippers and then following the trail of stars, which in this case disappears off the top of the screen. But the comet is supposed to be, I'm picturing it's going to be really low. And so I think one of the reasons my friends couldn't find it is that they weren't expecting it to be so low. And it really is down their ways. But that's what it's going to be like this weekend. Then the next think I'm a little bit off there. Then the next weekend, it'll be about that far along near the feet of the dipper. And then the weekend after that, it's going to be up a little higher. Of course, the sky is rotating down a little bit as this happens, but on the 23rd, it's going to get up pretty high if it stays intact. And then by August, though it's dimming throughout this time, it's going to get higher. And here's one of the things I'm really hoping to get is that maybe the comet will have two strong visible tails. And I forget why it has two tails. Perhaps Emma, you might know.
Come on, Dad. One's an ionized gas tail, and the other's a dust tail. The ion tail points away from the sun directly. The dust tail is pushed out by the sun by radiation pressure, but somewhat follows the path of the comet's orbit. I mean, come on, that's Comet 101.
Okay, Comet 101. All right, we got that. Anyway, so it might be a good opportunity to get two tails of a comet, either visually through a telescope or binoculars, and possibly in photography. Let's go on to the deep sky. I volunteered to do the What's Up for July, August, and September, and then I started realizing, wow, that's the thick of the Milky Way, and there's no way I can cover a lot of that in any one night. So I'm going to break it up. I'm going to just give you a little teaser about what's in this particular part of the sky. Here's another picture put together where I labeled a lot of these. I don't really have. Later, I'm going to come back with pictures of those in the August and September ones. But Emma, do you have a few highlights here that?
Oh, definitely. This is one of my favorite areas of the sky. You can see M20, the Trifid Nebula. That one's amazing. That has all three main types of nebulae in it. It's got a dark nebula, it's got an emission nebula, it's got a reflection nebula, all in the same nebula. So really cool. The Eagle Nebula up at the top, M17, is the site of the famous Pillars of Creation, where that we have active star formation. And the Omega Nebula just below it is also known as the Swan Nebula, and it actually looks like a swan, which is more than you can say for a lot of astronomical objects. You know, they don't actually usually look like what they're named after, but the Swan Nebula / Omega Nebula does. And I mean, my dad's right, you know, you could never really cover all of the amazing objects in this area with a single What's Up talk. There's just so many in this area. It's gorgeous.
And much to my embarrassment, I started here and realized I have hardly any pictures of these, and I don't even have, I discovered I don't even have pictures of M7 and M6. So I was thinking I'm going to just go to the north.
Dad, you don't have M6 and M7? That's like Messier 101.
Well, actually, not this time. It's not Messier, like Messier 101. Here's Messier 101, which just happens to be in the northern area, which we'll go to. We'll use that as a segue. Here's the view. I'm picturing that most of you are going to be out looking at the comet in the evening sky in July. And so you're going to need something to do after the comet sets. And so you'll have the Big Dipper here. And here's the bear and the Draco the dragon and the Little Dipper. And then if you take the Dipper and take the handle off of Alcor and Mizar and follow a little star hop of fairly bright stars there, that'll bring you very close to M101 or Messier 101. That's a kind of what is it, flat-on spiral galaxy. My friend Bob Nance photographed it here, and I just started trying it for the first time. And there it is from Wildomar, California, under a fairly light polluted sky. And that was my first attempt. But again, this particular view shows you about its field of view in a pair of binoculars. And I hope to do better. And now is the time to capture your last images of M101 before it starts getting too low into the sky to be an ideal object. Also, M51 is another good one to capture before it says goodbye for the year. I think, Emma, you've been able to see that one in a fairly small telescope, haven't you?
Oh yeah, that is gorgeous. And honestly, that's one of the really cool things about a small telescope. You know, most people assume that, you know, you need a larger telescope for deep sky imaging like this, but that's not the case. And I have a little 5-inch refractor that can bag most of these deep sky objects, M51, Dumbbell Nebula, Ring Nebula, you name it. You know, if you guys have just a little tiny telescope, don't be afraid to try to look at those deep sky objects, because they can look surprisingly good even in your little small scopes.
Yeah, and here's how the field of view would look comparable to a pair of binoculars, but it would never be that bright in a pair of binoculars. But this gives you an idea of how big of an object it is. If we go on from there, there's another object. One of the things I really enjoy doing, and I think a lot of you probably do this, if not, you certainly can, is I just like to take my camera, put it on the sky for a while, and then just look at the picture on the computer and figure out what's there. And I found a little cluster there, and I tried to figure out what that was. And I looked through like 4 different star charts, and some of them had something there and some of them had nothing there. And it turns out that that's the location, a possible location of Messier 102, which is either a catalog error or misnamed of NGC 5866. And so I'm going to get a picture of that one next, but I don't have one now, but I thought that was a very curiosity. Yes, Emma.
It's a very strange object, because if you do a Google search for it, like for just images of it, you get an edge-on galaxy like the sombrero, or you get just a face-on spiral that, like, you're viewing it from above. You know, Google can't make up its mind about what this object is. Kind of funky there.
Yeah. So M102, and then if we go a little farther toward the north, here's where the Little Dipper is, or the Little Bear, and there's where Draco the Dragon, and the Lyra, and then Hercules. My illustration of Hercules is a work in progress, but you know, who isn't a work in progress? And but this particular region of sky, with the exception of the bright star Vega in Lyra, is kind of vague, and I can never find Hercules easily. And the thing that I always find first in that whole area is this triangle. And I used to think that triangle must be the head of Draco the Dragon, but it's actually from the head of Draco the Dragon connecting to the foot of Hercules. But if you use that triangle, which I think pops out quite readily, I use it to find Draco when I don't have the dippers handy, when they're kind of out of the way, and I can use that to backtrack. But if you use that triangle and imagine kind of a mirror image of it almost, the other corner of that image will actually take you to an object you may be able to see on my screen in this wide field photo of a globular cluster, one that often gets overlooked because it's so close to the M13 globular cluster that people don't want to miss. But here's a small telescope view of M92 with broadband internet flying through it. And from there, we go to, I think, one of Emma's favorites. Got M13.
Oh, M13. That is a truly gorgeous globular cluster. In my opinion, a very representative globular cluster. If you want to know what they're all about, look to M13. I mean, I know there's a few that sometimes appear better, but this one is one of the easiest to find, in my opinion, and it looks gorgeous. So yeah, one of my favorite objects, also easily visible through either a small scope or a large scope, or binoculars, whatever you have on hand.
Yeah, so M13. Also, like just like with my wide field camera, I like to look at things and zoom in and discover things, but right next to M13, you may see another object shows up. I'm not trying to take world-class photos, mainly because I don't really want to spend a lot of time at the computer. To me, I use the camera as sort of an assisted observing tool, and then I just have a moment later that I can look at the pictures and go, oh, what's that? I'm gonna look a little deeper next time. So I hope to look a little deeper next time. And that's about where I'm going to stop. I've got a lot more objects to cover. This is just a teaser of where I'm going to pick up on the deep sky objects next month. And by then I hope to have some actual images of them so you can see about how big they are relative to a field of view of binoculars. Anything to add, Emma?
Oh, just that you know, M57, truly gorgeous, easily visible in a small scope as well. And most of these other objects, I mean, the North American Nebula might be a little hard to find. I mean, I couldn't even find it in like an 8-inch scope. Unless you're imaging, then you have more time to gather an exposure. But most of these objects are probably possible to catch and look very good in a small scope. So I wouldn't be discouraged just because they're like a deep sky or something.
Okay, I'll leave that as a teaser for the next presentation next month. And
good job, Dad. Leaving a teaser for the next presentation, that is like presentation 101. So proud.
Thank you very much, the Garrett team, for a very informative and entertaining presentation. I certainly learned a lot, and I'm going to use all the information to do my observing later tonight. Hi, my name is Reza, and I'm the Vice President of the club, reporting with a few seconds of delay from the International Space Station. I, too, in my own right, would like to welcome you to the July 11th, 2020 General Meeting of the Orange County Astronomers. Our meeting room is full, and I would like to make a shout out to our people at the overflow room at the YouTube. We are monitoring the chat there, so you can still ask your questions and send your comments there. So before we go to our main speaker tonight, first let me make sure everybody knows how to raise their hand, as we're going to use it to welcome our speaker in a moment. So can I have all the attendees to raise their hand virtually to make sure we're on par with that? Okay, we do have that. Excellent. Thank you very much. We're going to use that shortly. Second, I want you to take note of your channels of communication with us during this meeting. Go ahead and find out the Q&A option where you can ask questions from our speaker anytime about his presentation, and also use the chat option. I know a couple of you are using it already. That's great. To send us any comments you may have. Okay, so let's go ahead to the main talk here. Our speaker tonight was born and raised in Middletown, Connecticut, did his undergraduate work at the University of California, Riverside, received his PhD in physics in 2011 from Yale University, and took his postdoctoral positions at the University of Texas at Austin and the University of Washington. And now he's an assistant professor in the Physics and Astronomy Department at UC Riverside. Please join me by raising your hand in welcoming Dr. Anson D'Aloisio. Anson?
Thank you very much. And thank you very much for inviting me. It's my pleasure to be with you tonight. You know, when you invited me back in August of last year, I couldn't have imagined the situation that we'd find ourselves in now, but I'm glad we're able to get together online. I've been instructed by my wife to not talk too loud because my 4-month-old is sleeping next door. So I'll do my best, but hopefully I don't get into trouble. But yes, please feel free to interrupt if you have questions at any time. I think, can the moderator perhaps help me keep track of questions? I'm not going to really be looking at the chat probably for much of the talk. So just feel free to interrupt. Okay, so my main fields of study are theoretical cosmology and astrophysics. And very broadly speaking, I think, in my opinion, our chief goal in cosmology is to piece together the origin story of our universe. And so in this talk, I'm going to tell you just a little bit of what we know about our origin story. And it turns out we know quite a bit now. The progress in cosmology has been very rapid over the past few decades. So the first part of the talk is going to be a fairly broad sort of ground level overview. And in the last 15 minutes or so, I'll make a connection to some of the work that my research group has been doing at UC Riverside. So hopefully there's a little bit of something for everyone here in this talk. So in modern times, with the effect of light pollution from city lights, as you all know too well, it's easy to get the false impression that the night sky consists of a uniform random spattering of stars. But of course, that's not the case, and it becomes apparent even to the naked eye when you go spend the night someplace dark, like Joshua Tree or perhaps one of your dark sites. So this is an image taken in the mountains of Chile, where there are telescopes run by the European Southern Observatory. The distribution of stars in the sky is very structured, and of course, this is because we reside in our Milky Way galaxy. So this is an artist's rendition looking downwards onto the plane of the disk. We're out in one of the spiral arms looking towards the galactic center in this image here, which is about 26,000 light years away. And in this image, you can see, you're looking towards the galactic center here, and in the foreground, there's these clouds. These are not in our atmosphere, but rather they're interstellar clouds of gas and dust, which are obscuring the light from the stars. Now, modern technology has greatly accelerated our scientific progress in understanding the night sky, but perhaps at the cost of depriving much of humanity of this amazing view. And so I really think that the work that you do as an organization to remind the public of these wonders in the night sky is very important. So I'm going to thank you for that. But when astronomers look beyond the stars in our Milky Way, they see a universe that is teeming with other galaxies. There are galaxies of all different shapes, sizes, and colors. There are galaxies with just thousands of stars, and there are some with hundreds of billions of stars. There are boring galaxies that look just like big smudges, like the galaxy at the top of this diagram here. And there are others with beautiful, structured, and colorful spiral arms, such as the galaxies down here. And it turns out that the galaxies are arranged in a vast web of structure that we call the cosmic web. So on the right here, this animation, this is an image. It shows a map of our universe compiled with telescopes located in the mountains of New Mexico. And each one of these points is an individual galaxy with perhaps hundreds of billions of stars of their own contained within them. We're at the center of the map, and you get further away as you extend radially from the center. In a sense, you can think of galaxies as being a kind of fundamental unit in our universe. In this picture, each galaxy is like a tiny particle that traces out the large-scale structure of our universe. And in fact, the universe is highly structured on large scales. You can see in this map here that there is really a web-like structure punctuated by these huge cosmological voids. At the nodes of the web are massive structures, clusters of galaxies, clusters of thousands of galaxies. So it really is an exquisitely structured, large-scale universe that we live in. But one of the greatest insights that astronomers had in the last century, in fact, I would even elevate that to say that one of the greatest insights in all of human history is that the universe didn't always look this way. Okay, so now how were astronomers able to see that the universe didn't always look this way? How are they able to see the universe as it looked long ago? So in our everyday lives, we're used to seeing things happen in real time. For example, when I wave my hand, you take for granted, if I were there in the room with you, you would take for granted that you're seeing it immediately as it happens. But actually, there is some finite time for light to travel between my hand and your eye. But for those distances, the light time travel is just very, very short. But the distances to other galaxies in our universe are so enormous that their light can take millions or up to 13 billion years to reach us. And at first that seems like an annoyance, but actually this turns out to be very useful because our telescopes effectively become like time machines as we look further away. The further away we look with them, the further back in time we're able to see. And if we train our telescopes on the darkest patches of the sky, what we think are the darkest patches of the sky, we can see galaxies as they look near the beginning of time. So this image here is a composite image taken by the Hubble Space Telescope. Some of the tiny specks in this image are actually among the earliest known galaxies in our universe. And just for reference, one side of this image subtends an angle that's about 1/10 the angle subtended by the full moon. So it's really a quite tiny patch of the sky. Even in this dark, tiny patch of the sky, if you stare at that patch long enough, you start to uncover many, many galaxies. You actually begin to see some of the earliest galaxies that formed in our universe. Analyzing this image, and I think astronomers have now detected tens of thousands of galaxies in this image alone. Analyzing this image has revealed that galaxies, on average, seem to get smaller and dimmer as you go backwards in time. In fact, if we zoom in on one of the tiny specks in these images, this image here is sort of a zoom in of one of those specks. It's an object called GNZ11. And this is the earliest confirmed galaxy to date that we know of. So this image shows how this galaxy looked approximately 13 billion years ago. In other words, it took light 13 billion years from this galaxy to reach us today. And this was imaged by the Hubble Space Telescope. And this object, GNZ11, it turns out to be vastly different from the galaxies we know today. So for one thing, this is one of the biggest galaxies that existed in that early universe. And it's still only 1/25th the size of the typical present day galaxy. So this is not to scale. This has been blown up. Really, this object is much, much smaller than the typical present day galaxy. At the same time, astronomers have measured the rate at which it's forming stars, and it happens to be doing that at a rate that's 20 times faster than the typical galaxy today. So it's assembling itself at a remarkable rate. So the main point I'm trying to drive home here is that the galaxy population has really evolved significantly throughout the age of our universe. Galaxies that we see in our present day universe don't look the same as galaxies that we see further back in time. And if we look even further away, we can observe all the way back to a time before galaxies existed. So near the beginning of time, this is what the universe looked like. Now it's not exactly, this is not a true color. This is not how it would look to the human eye. The coloring is false. But the point that I'm trying to impress upon you is that the early universe before galaxies formed was very smooth and featureless. And so this is actually, this would be the cosmic microwave background as the universe looked when it was only 400,000 years old. So we think it's about 13.8 billion years old today. This is really the universe in its infancy. Actually, high precision measurements of the cosmic microwave background reveal that there were very tiny splotches, but they were extremely tiny. So the variation in these splotches in the cosmic microwave background reflect variations in the amount of matter from location to location. So for example, the amount of matter over here varies from the amount of matter over here by about 1 part in 100,000. So it's an extremely, extremely tiny variations, but we're now able to measure these variations very precisely. And in fact, the small scale splotches that you see in this map of the cosmic microwave background, according to our modern understanding, or what's called the standard model of cosmology, these are the precursors to galaxies in large scale structure in our universe. And so I'll discuss this more in just a little bit. These are really like the seeds of the galaxies that you're observing today. So a major outstanding question in modern cosmology is, how did the laws of physics take the early universe and transform it into this? So in other words, how did the laws of physics take this primordial soup that's very homogeneous and isotropic and transform it into these exquisite galaxies with these beautiful spiral arms that we see today? That is a central question in our field. Now, to address this question, astronomers are using snapshots of the galaxy population at various times in the history of our universe to try to figure out how present-day galaxies were assembled. And they've made great strides in understanding galaxies this way. So for example, here's a snapshot of a typical present-day galaxy. If we go back a few billion years, we have now acquired many snapshots of galaxies that from long ago. And if we go further back, so this is the earliest snapshot of a galaxy that we have today. So we try, take these snapshots and try to understand the relationships between them. But the earliest part of the story is missing because we can't yet observe the first galaxies to form. They're simply too small and dim to be seen with current technology. So remember this earliest object, GNZ11, I mentioned that it was one of the biggest galaxies at this point in the history of the universe. So in that sense, it was very atypical for this time period. And in fact, in our theories, we expect there to be many more smaller and dimmer galaxies that existed at this time. So this object GNZ11 is far from a representative sample of the typical galaxies that existed at this time. And so this lack of our ability to probe the most typical galaxies at these times is a significant limitation in our understanding of how galaxies form in our universe. So to make an analogy, the situation is like, trying to understand human beings without any knowledge of childhood. We can take snapshots of adolescents and teenagers and adults, and we can make great progress in understanding human development that way. But our understanding would always be limited until we have a complete, until we have snapshots of children, of babies and infants too. Okay, we have to understand early. In order to really fully understand the human, you have to understand the earliest of stages of human development. And in that sense, we don't understand the earliest stages of galaxy development, let alone galaxy formation in more recent times. So in a sense, one of the major goals of astronomy in the coming years is trying to understand the childhood years of galaxy formation. Now, I just said that our understanding of galaxy formation is incomplete because of the status of our observations, but we're not completely in the dark on this topic because we do have theories for how the earliest galaxies formed. And those theories have really, instructed us and sort of motivated our missions for building the next generation telescopes. And so let me describe our best theoretical model for this process of galaxy formation that we have. And I can't tell this story without first telling you a little something about dark matter. So, over many decades of research, there has accumulated a very convincing evidence that there is an unknown type of matter in the universe, which I'm sure many of you have learned a lot about. So this unknown matter doesn't interact with light, as far as we can tell, and so we cannot see it directly, but we can observe its significant gravitational effects on the matter in our universe, and in fact, even the expansion history of our universe. And so we call this this unknown matter dark matter, even though perhaps a better name for it would have been invisible matter, but admittedly that's sort of less snappy than dark matter. So we use the term dark matter. So dark matter makes up the majority of mass in our universe. And in fact, cosmologists have now measured it, the fraction of the mass that it makes up very precisely. And it takes up about 80% of the total mass in our universe, with the rest of the mass being mainly in the form of hydrogen gas and also helium gas. And it's because of this dominance in the mass that the dark matter really drives the galaxy formation process. So remember, these tiny splotches in the cosmic microwave background that I referred to before. The gravity of the dark matter causes these tiny splotches to start collapsing inward on themselves. So regions where there was slightly more matter on average starts to gather more and more matter over time. And regions that were underdense, start to become more and more evacuated over time. And gravity causes, this situation is unstable because of the presence of galaxies. So gravity causes this instability, which is known as gravitational instability. And these tiny splotches begin to coalesce, to collapse inwards on themselves. Over time, gravitational instability transforms those primordial splotches into a nascent cosmic web. And so this image here on the left shows a snapshot from a simulation, supercomputer simulation that I ran of structure formation in the universe. You can see that. So this is what we do is we randomly draw a simulated universe from the probability distributions that are statistically consistent with our measurements, our cosmological measurements of the cosmic microwave background. So in a way, we're kind of rolling the dice to draw a separate universe, if you will. And then we run those initial conditions forward in time using the known laws of physics to sort of see how structure forms. And we get out of it sort of a cosmic web that forms. At the intersections of the web are dense clumps of dark matter, which we call dark matter halos. And again, this is a bit of a misnomer. It's not a halo in the sense of like an angel halo rather, but it's like really you can think of it as like just a dense clump, essentially concentrated, dense clump, quasi-equilibrium clump of dark matter. So these early dark matter halos weigh about 1 million times the mass of our sun. And we think that these halos are the formation sites of the very first galaxies. And so let me describe to you now, and give you a rough schematic, a sort of crude picture for how we think that happens. Okay, so this is the dark matter halo weighing about 1 million times the mass of our sun. This is matter that you would not be able to see. It's all dark matter. And the gravity of that massive dark matter halo causes gas inside the nascent cosmic web to be attracted inwards. Okay, so the halos gravitationally attract the hydrogen and helium gas into them. The gas over time falls into the dark matter halo and it begins to cool. And how it cools is actually, it's related to the microphysical processes of the gas particles. So kind of paradoxically, in order to get gas to cool, you need to actually heat it up. As this gas is falling into the halo, the compression of the gas causes it to heat up. And because it's getting hotter, the particles of hydrogen atoms, they randomly bump into each other more often and with more energy. And they actually excite the electronic energy levels of the hydrogen atoms. But the hydrogen atoms want to be in their ground state. And so when they decay, they emit photons. And these photons then carry away some of that energy of the gas. This is what we call radiative cooling. Okay, so the gas kind of radiates away its energy, and it becomes more efficient if you heat it up to higher temperatures. Okay, so part of what drives the cooling of this gas is actually the falling inwards into the halo. Now the cooling gas breaks up or fragments into smaller, denser clouds that start to undergo their own runaway gravitational collapse. So basically, when you have a cloud of gas and parts of it are cooling on very short time scales, much shorter than sort of the dynamical time of the gas cloud, this is an unstable situation. And what ends up happening is you get dense clumps that form and fragment out of it. And then it starts to undergo its own runaway gravitational collapse. So these tiny clouds of gas get so dense that nuclear reactions are ignited within them. And when that happens, the very first stars form. And so for the very first time in the history of our universe, there is starlight inside of these million solar mass halos that existed in the early universe. And the emergence of the very first starlight has profound consequences for the universe as a whole. So before there was starlight, the universe was permeated with cold hydrogen gas. But when the first stars formed, their starlight penetrated outwards into the cold gas in between the galaxies, ripping apart electrons from their atoms and heating up the universe. So this movie that I'm showing you is a computer simulation of the starlight from the very first galaxies moving out into the fog of cold gas, ionizing and heating it up in a patchy way. So this lifting of that cold neutral hydrogen fog is what's known as reionization. Okay? And it's a major phase change for the entire universe. That starlight ends up affecting almost every hydrogen atom in our universe. So the formation of the first stars was a major milestone in the evolution of our universe as a whole. The bulk of the universe went from being cold and neutral to hot and ionized. And we think that this process, started to take place when the universe was a few 100 million years old and was largely completed by the time the universe was 1 billion years old. And again, we think the universe is about 13.8 billion years old today. Okay, but then how do we end up with such elaborate galaxies like these spiral galaxies? So the first galaxies formed in small dark matter halos, as I said, million solar mass dark matter halos. Our Milky Way sits inside of a dark matter halo that's more like 10 to the 12 solar masses. But over time, those tiny halos began to accrete matter gravitationally again, and they merged with other halos to form bigger halos. And then these intermediate halos merged with other halos to form yet bigger halos. Okay, so over billions of years of cosmic time, the present day galaxies are assembled in this sort of hierarchical process. Okay, and note that this theoretical model that we have for how galaxies form explains naturally why it is that when we look further back in time, the galaxies look intrinsically smaller and smaller as we go. The earliest galaxies were very tiny, and that is explained by this hierarchical assembly process. And that's consistent with, if you just took those splotches that we observe in the cosmic microwave background and evolve it forward using the laws of physics and assuming some things about the nature of dark matter, you end up getting this hierarchical process. So that's one of the reasons why we believe we know something about the properties of the dark matter. Okay, so that's all fine and dandy, but how are we going to confirm or refute this model in the future? This is a scientific model, and it's, astronomy is a scientific discipline. And so you could have the most beautiful and elaborate model, but it's worthless unless you can test it against observations and measurements. And so now I want to talk about a little bit about what the next decade is going to bring in terms of new observations. And I'm going to highlight just one. There's many different observatories that are coming online with a science goal to explore this epoch of early galaxy formation, but I'm going to highlight just one of those. So the Hubble Space Telescope, which was launched almost 19 years ago, I believe, has really transformed our view of the universe and our place in it. So not only did it give us the most distant view of the universe so far, well, not the most distant view, but the most distant galaxy that we've detected so far, but it's also brought us these amazing, images within our own galaxy. I'm sure you're all familiar. Actually, it was mentioned in the What's Up presentation. This famous pillars of creation image from Hubble, and as it was also mentioned earlier, these are plumes of interstellar gas and dust within which new stars are being born. It's kind of a stellar nursery. And these images have a great impact on the public and their imagination and appreciation for science. And actually the starlight from those new stars are illuminating, actually ionizing and evaporating the gas in these pillars, somewhat analogously to that reionization process that I was talking about earlier, except that reionization process happens in the intergalactic medium, the space between the galaxies. But I think NASA's next generation space telescope is really going to knock our socks off. And of course, Hubble's successor is the James Webb Space Telescope. And this is a life-size model of the JWST that I was fortunate enough to see because I was a postdoc at the University of Texas in Austin, and when it was on tour, and it actually made a visit to the South by Southwest festival in Austin, which is held every March, and they had it on display there. It was really awe-inspiring to see it, the size of it. So it has a bigger mirror than Hubble, so which will make it more sensitive. But the most important new feature is that this is an infrared telescope. And that's important because the further away we look, the redder the galaxies get. And this is an effect of our expanding universe. A common analogy that is made to describe the expanding universe is an inflating balloon. So imagine that we live on a two-dimensional surface of the balloon. We have no knowledge of anything outside of that two-dimensional surface. We're not even aware of the third dimension. This is a flawed analogy because there is no sense in which you can embed, at least we think, there's no evidence to believe that that you can embed our four-dimensional space-time into a higher dimensionality. So to try to think about a higher dimensionality in which our four-dimensional space-time is embedded is not necessarily correct. But nonetheless, it's a useful analogy here with the balloon. So if you're sitting on the two-dimensional surface of the balloon, and if I inflate the balloon, the distance between 2 points on the balloon will naturally increase with time, 2 reference points. And analogously, space itself is expanding with time. This is a natural consequence of Einstein's general theory of relativity. It's sort of inevitable that space is dynamic. And so you can imagine then if we had galaxies sort of spattered onto the surface of the balloon, on average, the distance between the galaxies would be increasing with time as the universe expands. And we see that. This is Hubble, the famous Hubble law, that on average, galaxies are receding away from us. And this expansion of the space, in addition to spreading the galaxies out, it also stretches out the wavelength of the light, which makes it redder. So as the light is traveling through this expanding space-time, the wavelength is actually being stretched out. The further away an object is, the more expanding space it has to travel through to get to us. So the redder it will appear. And so the infrared capabilities of JWST will allow us to see significantly further back in time than Hubble could. Hubble could not, there's a horizon beyond which Hubble is not really optimal for seeing galaxies. So with JWST, we'll be able to really push that frontier of observations forward, or rather I should say backwards in time, well into the era when we think the first galaxies are forming. And so we'll start to uncover more and more of the earliest galaxies. And we'll start to begin to test the theoretical framework that I described earlier, how we understand the galaxy formation process. In a way, we'll finally be able to start, filling in more of the childhood and perhaps baby pictures of galaxies in our universe. And we'll be able to start to piece together, the development of galaxies over time. Okay, so I just talked about, the efforts to detect and characterize more of the first galaxies directly with a telescope that resolves them and can take spectra of them. But what I failed to mention there is that even with the JWST, we won't be able to detect a large fraction of the first galaxies. If our models of hierarchical assembly are correct, many of those galaxies are still too small and too dim for us to be able to see with JWST, and in fact, in the foreseeable future. And so that's a little bit of a more pessimistic take on the next decade, or this decade rather. So are we stuck? Is there anything that we can do? And it turns out that there is. We can study these elusive galaxies, these tiniest galaxies, by observing their impact on the gas and the space between the galaxies, what I referred to earlier as the intergalactic medium. So for now, I'm just going to refer to it as the IGM for short. So recall this reionization phase transition that I described earlier that occurs when the first galaxies form. It's driven by their starlight. If we could see the intergalactic hydrogen and how its ionization state and temperature changes during the reionization process, we could try to understand some of the properties of those tiniest galaxies, albeit indirectly. Okay, so we can indirectly observe the impact of those galaxies on the universe by studying the reionization process, if we could only see the intergalactic hydrogen. The problem is that the IGM is very diffuse, and the hydrogen atoms don't emit light at wavelengths that we can observe with our optical and infrared telescopes. So, as you know, if we don't receive any photons at our telescopes from these clouds, how can we see them? So fortunately, nature is very kind in this regard. So nature provides us with these very bright light bulbs that we call quasars. So quasars are cosmological sources. They reside outside of our galaxy. They were first discovered in the early 60s. And over time, it took a while, as science always does. The march of science is slow at times. But within that decade, it was understood that these quasars were cosmological. They were outside of our galaxy. And in fact, they can be found throughout our universe. Quasars are some of the earliest objects that we see in our universe. So their intense radiation is produced by hot gas that's in the process of falling into supermassive black holes at the centers of distant galaxies. So you have a galaxy, and we think that there's good evidence to believe that all luminous galaxies today have a supermassive black hole at their center. And in fact, the formation of the supermassive black hole go hand in hand with the formation of the galaxies. So what you have is you got a supermassive black hole at the center of a distant galaxy, and it's vigorously accreting gas. And this gas gets heated up to extremely hot temperatures as it's falling in. And the friction in the gas, that's what causes it to heat up, actually causes the gas to glow very brightly in a manner that actually can outshine the total energy output of all of the stars in the host galaxy. And it's because of this great intensity that we can see the light out to very great distances. So as light from a quasar passes, it's way out there in the universe, it's traveling through the IGM, it passes through a cloud of hydrogen gas on its way to our telescopes. The electronic transitions in the hydrogen atoms imprint absorption lines in the spectrum of the light. By far, the most important of these electronic transitions is the Lyman series, or transitions from the ground state of the hydrogen atom transitions from to the ground state of the hydrogen atoms. So for example, Lyman alpha corresponds to jumps between 2 to 1. Lyman beta is jumps between 3 to 1, and so on and so forth. There's a whole series of these lines. So what happens is light from a distant quasar hits hydrogen atoms in the intervening gas cloud. And for example, Lyman alpha photons are photons with just the right energy to make the transition from the n equals 1 to n equals 2 state, excites the atoms. But of course, the atoms, as I said before, they like to be in their ground state. And so they're going to decay to the n equals 1 state. And when they return to ground, they emit photons. And the decay photons are emitted in random directions. So they get, effectively get scattered out of the light, and those photons of that particular wavelength don't make it to our telescope. And the absence of those photons creates these absorption features in our spectrum, which allows us to, it's a characteristic fingerprint that allows us to identify the presence of neutral hydrogen in the IGM, in the space between us and the quasar. It's effectively like casting a shadow at certain wavelengths. Now there's a complication to this simple picture. So remember I said that the universe expands. As light travels towards us, it gets redshifted by the expansion. And so the location of the Lyman alpha absorption line is different for different hydrogen clouds along the line of sight. And I'm going to show a movie that illustrates this very nicely. So in this movie, the quasar is depicted by this bright blob in the upper left-hand corner. The light from the quasar starts out with some intrinsically smooth spectrum with the characteristic shape. So what I'm showing here on the x-axis is wavelength, and on the y-axis is the intensity of the light that you're receiving at your telescope. These vertical lines here and here show the wavelengths corresponding to the Lyman alpha transition and the Lyman beta transition. And then there are a number of other transitions for heavier elements that are shown in the colors here. So now I'm going to play the movie, and when I do, you'll see that the spectrum shifts to the right with time, or towards longer wavelengths. That's the effect of the expansion of the universe. And as the light passes clouds of neutral hydrogen, you'll see that the absorption lines are being imprinted at different locations in the spectrum. So every now and then you might pass a very dense cloud of hydrogen like a galaxy, and you get, in that case, you get a very deep absorption feature, a sort of a characteristic shape. These are called damped Lyman alpha systems. Okay, so the series of lines that are blueward in wavelength from the intrinsic Lyman alpha emission line of the quasar, this big bump here, but redward of the bump corresponding to Lyman beta, so in other words, the fine sort of the small absorption features in this part of the spectrum, it's what's called the Lyman alpha forest. And it's called that because the series of absorption lines resembles a forest of trees, right? And this forest, you really can think of it, it's like keeping record of the hydrogen that's encountered by the light as it traveled towards us, through the intergalactic space. It's like, think about a record player, it's really, cutting a record. It's like imprinting grooves in the record. And because it's like this sort of record of the hydrogen gas, it's really an extremely powerful tool for studying the reionization process. So how do we use the Lyman alpha forest to study reionization? So on the left here, I'm showing real, this is real data now, just a sample of quasar spectra. Where these sort of jagged regions here are the Lyman alpha forest parts of these spectra. And these quasars, these are snapshots of the quasars when they existed, when the universe was earlier than a billion years old, younger than a billion years old. So these are very distant quasars. So one of the ways that we use these Lyman alpha forest spectra to probe reionization has to do with the fact that even trace amounts of hydrogen atoms, hydrogen in its atomic form, we call it neutral hydrogen. Even trace amounts of neutral hydrogen in the IgM is enough to cause complete absorption in the Lyman alpha forest. So for example, when the universe was about a billion years old, and here I'm quoting a cosmological redshift. For those of you that are familiar with cosmology, this Z is what we call redshift of 6. Or just think of this as like when the universe was a billion years old. If as little as 2 parts in 100,000 of the hydrogen atoms are in their atomic state or in their neutral state, it's enough to block 99% of the light in the Lyman alpha forest. So we can just take these spectra of these quasars and we can go out into the forest. And if we see even a tiny amount of flux in the forest, so a tiny amount of transmission in the forest, we know that that patch of the universe had to have been reionized by that time. So again, the fact you can look at these spectra corresponding to a snapshot of the universe when it was about a billion years old, and you can see that most of these segments of the Lyman alpha forest do indeed show even just a little bit of transmission. And so for that reason, we kind of know that the reionization process had to have been largely complete by the time the universe was a billion years old. That's the basis for that statement that I made earlier, to say that we think that that phase transition of reionization had to have happened before the universe was a billion years old or so. And that really puts constraints on when the first galaxies formed, because we know that we think that the first galaxies really drove that reionization process. And this tells us that process was done by the time the universe was a billion years old. So therefore, the first galaxies had to have formed before, quite a bit before that time. But our most recent insight into this field is actually that the patchiness of the high redshift Lyman alpha forest might be telling us something deeper about reionization. So note how different the forest looks for different quasar sightlines. So each one of these is a different quasar out in the sky. So in some quasars, you've got what could be described as islands of transmission in the Lyman alpha forest, like over here. Whereas in others, you've got lots of transmission throughout the forest. And then in yet others, you've got dark, large dark gaps with no flux at all in the forest, for example, here. So there's a kind of characteristic patchiness to these spectra. And in fact, it turns out that we think that this patchiness is telling us something about randomization. What causes this patchiness? So one of the most exciting ideas to come out in this field recently is that these sightline to sightline variations in the quasar spectra might be a direct consequence of reanimation's patchiness. So suppose we're over here, these are our telescopes, and you can imagine that, this sightline that has transmission throughout the forest corresponds to looking at a quasar in this galaxy over here. So that this sightline, it's mostly ionized all the way through. It doesn't pass through any clouds of neutral hydrogen. Whereas you could imagine this sightline, which has this long gap here, corresponds to looking at a quasar sitting in that galaxy, and that sightline passes through a substantial patch of neutral gas. So the brown regions would be the neutral gas in the IGM. Okay. So now I should note that our sample of quasars at these redshift now consists of about 200 quasars. And so I've just shown here a small illustrative sample. So we have statistically compared the observed fluctuations in the forest to simulations of the Lyman alpha forest in our models of patchy reionization. And a very plausible explanation for these observations is that we're actually probing the tail end of this global phase transition that we call reionization, which, remember, we think is driven by the first generation of galaxies. So this is an exciting prospect, the idea that we could be actually probing the tail end of this reionization process with our quasar spectra. But we're not sure it's the correct explanation just yet. We've got a lot of work to do to either confirm or refute it. Remember, I said that the march of science is slow at times, and but it's a plausible hypothesis. And so this is ongoing work that's being done by my research group at UC Riverside, and we're involved more so on the theoretical side of things, running supercomputer simulations of early galaxy formation and the reionization process, and making synthetic Lyman alpha forest spectra and comparing the statistics of those spectra to the spectra that are actually observed. And the exciting thing is that in this decade, in the next few years, our sample of high redshift quasars is going to explode. We're going to get many, many, many more of them. And the reason for that is that there are these huge cosmological surveys that are surveying huge swaths of the sky just to get a statistical map of our universe. And these surveys are going to uncover tens of thousands of quasars at these redshifts. And what we'll have to do is then follow up those quasars with with other telescopes that have high resolution spectrographs on them. So not all of those tens of thousands of quasars are going to be able to give us high quality Lyman alpha forest spectra, but we'll increase our sample by a whole lot. And so we'll actually have a lot more data in order to make more definitive statements about this. Okay, so just to conclude, the present day universe rather is teeming with galaxies of all different shapes, sizes, and colors. But one of the greatest advances, I think, in human history is the discovery that it wasn't always that way. And in fact, there was a time when galaxies didn't exist. And astronomers are trying to understand how and when the very first galaxies formed. I just described how studying reionization of the intergalactic medium will help shed light on the nature of the first galaxies. And in fact, there's tentative evidence that we've detected the tail end of that reionization process, which is being driven by the formation of the first galaxies. New telescopes are being built that will allow us to detect directly some of those earliest galaxies. And so this decade, because there's also many other observatories coming online, this decade will be a very exciting time for this active field. Thank you.
Thank you very much for a very, very nice talk. Well, we have all audience applause you. We are all at awe. Thank you very much. Thank you very much.
It's my pleasure.
So we have some question. Now the floor is open for questions. We could use the Q&A option to ask your questions. And by the way, Anton, we do see the controls, Zoom controls on your screen. Maybe can you click on the slide?
So you see all of the controls?
Yes,
here?
well, we're seeing that. At the middle of the presentation, it appeared, and I didn't want to interrupt you.
Oh.
Well, okay.
Yeah, I don't, let's see.
Let's see if you click, okay.
This,
if you click on the presentation itself, does it hide it or?
No, it doesn't, unfortunately.
No, okay. Well, maybe if you stop share and then you do that again.
Okay.
Okay, so we have some questions for you already. First of all, is the question about the very first few slides when you showed the image of the matter dispersity in the universe. They are all wedges, right? And the question is why did you like wedge rather than like a complete sphere?
Sure. Let me put that image up because let's see here. Yeah, so I think you're talking about this image, right?
Yes.
Yeah, so this just has to do, so that there's no need to worry. The universe doesn't have these huge wedges that you might fall off into, but it's really that there are certain parts of the night sky that are not accessible for these observations. And I'm not exactly sure because I'm not an observer who worked on this particular survey. This is the Sloan Digital Sky Survey these results come from. But part of it has to do with the location of the telescopes. Some of it might have to do with foreground in the night sky, like our galaxy. But for certain reasons, there are not patches that are optimal for, or even accessible for the telescopes to look at. Being in New Mexico, being in the northern hemisphere is one effect. So yeah, that's the deal with that.
Okay, thank you. And then we have another question about the James Webb Telescope compared to the Hubble.
Right.
How much of the size difference between JWT and Hubble is lessened by the lower frequency used by the JWT? The same size mirror, lower frequencies should give dimmer pictures by some amount.
Yeah, that's a good question. I suspect that the increase in size outweighs that. It's not, I mean, the JWST has a near infrared instrument and a mid infrared instrument. And so I don't think that the longer wavelength plays that much of a role. I mean, it is a counter effect, but I think we will get, if I remember correctly, sort of roughly the same angular resolution as the Hubble. So it's not that we're not going to get worse angular resolution than the Hubble, but in fact we'll get about the same angular resolution, except now we'll be able to see in infrared. So I think I don't know if that answered your question. Unfortunately, I'm not an expert in sort of the instrumental and observational. So I can guarantee you all know more about actual observations than I do. I sit there with paper and pencil and coding on supercomputers and stuff most of my time. So.
Thank you. Okay, next question is the questionnaire says, is there a relatively simple explanation for the planar structure in the universe map, and does it involve angular momentum analogous to the planar structure of the solar system, galaxies, etc.?
Oh yeah, so the universe doesn't have a planar structure to it, and that again, I think that's related to the first question. That this is not a full map of the universe. If you were to make a full map, it would be fully spherical. And on large scales, the universe is on large enough scales, the universe looks homogeneous and isotropic. This is something called the cosmological principle. So there is actually a higher degree of symmetry in our universe in that sense. And So there is no effect in that regard. There is, the nature of this structure is related to the physics of gravitational collapse. So what you find is that the early splotches in the universe collapse first along one dimension, and then another dimension, and then a third dimension. So you do end up getting pancake-like structures in the early universe, and then filament-like structures, and then halos would be like the last, kind of node-like structures. So you do end up with pancake-like structures in the universe, but that's only because of the gravitational collapse. But it's not really related to the spiral structure of galaxies, which is a conservation of angular momentum phenomena.
Thank you. And the next question is about the cosmic microwave background image you showed. The questioner says that he understands the predictions of cosmic microwave background have been off by a factor of 10. And then he says the Big Bang model has not been abandoned. So what was done with this error in prediction?
So I'm actually not familiar with, I'm not sure what you mean by off by a factor of 10. You may be referring historically. So what is it that's a factor of 10? Do you mean that the temperature of the CMB?
Well, the questioner has not elaborated. Maybe we could ask him to elaborate more.
Well,
about
yeah.
that.
So I can begin to answer what I think the question is that it is true that in the earliest part of the story, before the cosmic microwave background was observed in the 60s, cosmologists worked out that for the Big Bang model, there ought to be this relic of a time when the universe was much denser and hotter. And this, what the cosmic microwave background is a black body, what's called a black body spectrum, which is the characteristic spectrum that you get from matter when it's in thermal equilibrium with photons. And so it tells us that the universe was once denser and hotter, such that there was an equilibrium between all the species in the universe. And so, yeah, cosmologists had sort of realized that would be a consequence of the model. But in those earliest days, they really had no observations to guide them into like what the actual parameters of our universe are. So there was a wide range of possibilities. The most robust statement they could make was that there ought to be this black body spectrum, but they didn't really know exactly what temperature that black body spectrum would appear to be. And so, yeah, there was large uncertainties. Maybe they picked a favorite model and they said, here's where it should be. It was detected, and then of course our vision, our understanding is refined, and then our models get refined. And so, huge errors like that are really part of the scientific process. And sometimes those errors cause us to abandon models. If something is just wrong, if the idea is wrong, then we certainly abandon them. And we don't hear about those ideas anymore. If you go back in the literature, it's just littered with all these wrong ideas, but we forget about them. And maybe that's a good thing, because we move on from bad ideas in science. When we detected it, and actually the black body, the idea that there's a black body spectrum was right. Maybe what temperature that spectrum should be at was wrong. But so that refines our model. So it doesn't the fact that it was off doesn't invalidate the model, but rather refines it. And so that's why, and in fact, since then there's lots of other pieces of independent evidence that all point to a consistent model of our universe. And that's why we believe it. The science is really a lot like being like legal work. You build a case based on multiple lines of independent evidence. You build the best case you can. And when you've proven to yourself beyond a reasonable doubt that this thing is right, then you say, okay, I believe that thing. Of course, that doesn't, further down the line, we might find other evidence that invalidates the model. But what usually happens is some aspects of the model remain correct, and we have to revise the model and improve it to account for that additional evidence. So anyways, that's just sort of my spiel on sort of the scientific process, but I hope that answered your question. I'm not sure if it did.
Thank you. Well, let me, okay. So the next questioner has praised your presentation, and his question is, you know, you mentioned about the capabilities of JWP, and generally every decade or so, our instruments become more powerful and we could see more and more. The question is, how long can this continue? Will we ever get to see the edge of the universe?
Well, in a sense, we have seen an edge, which is the horizon beyond which we can't see anymore, at least with light, with electromagnetic radiation, and that is the CMB, because the CMB is really like a surface. It's like a horizon beyond which we cannot see anymore, because the universe becomes opaque when it, you know, that the CMB corresponds to another phase transition in our universe, where if you go further back in time, the universe is so hot that the universe is a plasma, and the photons then are just scattering around many times. So it becomes kind of like, you know, like opaque, and so in that sense, we can't see anything earlier than 400,000 years old when the CMB was emitted. On the other hand, we might be able to see earlier than that if we look at other particles besides light, besides photons. You know, for example, there is a cosmic background of neutrinos, and neutrinos decoupled from the rest of the matter much earlier than the photons did, because the neutrinos interact very weakly with other particles. So if we had the technology to be able to detect the neutrino background, that would be probing the time much earlier than the CMB. And so in that sense, we'd be looking further back in time. That would expand our horizon further. And then another avenue is through gravitational waves. Gravitational radiation would allow us, if we were able to detect the kind of gravitational waves that get emitted a tiny fraction after t equals 0 in the Big Bang model, that would give us insights into the very earliest stages of our universe. So yeah, I think, you know, to me at least, I'm optimistic about the expanding of the horizons being very plausible. Maybe not within my lifetime, but I possibly within my lifetime. And so I do think it could go on. I guess this depends on humanity, you know, like whether we're still around to do it. But that's just my take on things.
Thank you. The next question asks, are dark matter halos still merging? Can we expect even bigger galaxies in the future?
Yes, in fact, you know, Andromeda, I forget now the time scale. Has to be, you know, hundreds of millions of years at least. But you know, Andromeda is on its way to merging with the Milky Way, and so our dark matter halos are in the process of merging. And yeah, things are constantly accreting and merging, and the galaxies will grow over time. But the thing is, that's not necessarily the same as the visible parts of the galaxy getting bigger. That depends on whether the galaxy is acquiring fuel to constantly form stars. And there are, you know, as you grow the galaxy, there are mechanisms which actually cause the star formation to cease. And in that sense, the number of stars in the galaxy doesn't grow, except through mergers. But you know, stars die too, so you're losing stars over time. So yes, we will continue to see bigger galaxies. What we may not continue to see over time is the formation of bigger structures in our universe than galaxy clusters, and that's related to something called dark energy. So the universe is undergoing now, in a sense, an acceleration in its expansion. And that is actually causing structures larger than galaxy clusters to sort of cease forming. So in that sense, there are certain features of the large scale structure is being frozen out in a way. But that's related to dark energy, which I didn't talk about today.
Thank you. And the next question, does a structural density of the observable universe drop off for the larger structural sizes? In other words, does a structure have a size limit?
Does the structure have a size? Well, I think I did touch upon that a little bit, which is to say that that depends on the expansion history of the universe, and we've entered now into a phase where the expansion is being dominated by the presence of dark energy, and that's actually cutting off new structures on galaxy cluster scales from forming, or it will in the future if we understand dark energy. Of course, we don't understand very much about dark energy, but it could be that we're wrong about that. But and also the densities. So I don't know if this is related to what the person was asking, but the densities of the structures actually retain memory from the epoch when they formed. So earlier structures, earlier galaxies formed at a time when the universe was denser, and they are on average denser because of that, because they retain a memory of that initial density. Whereas the density today is lower than it was back then. I don't know if that answered the question.
Oh, okay. I hope it did. Thank you. The next person asked a question and wants clarification on how you use the simulation data with the real data, and how do you compare them, and how do you make sure that your simulation is correct?
Yeah, that's a great question. So what we do is we run, as I said before, I'll speak specifically about the Lyman alpha forest, which is where I use the context where I use that. We run these simulations of the large scale universe and the formation of the cosmic web. And then we trace sight lines. We actually trace skewers to the simulation box. And we then use the data from those sight lines to construct a mock Lyman alpha forest measurement. And then we add things about the instrument, like for example, we add noise. We try to replicate as close as we can reasonably to what an actual measurement would look like. And we do this for different models of our universe, or different models of reionization, for example. We have different simulations where reionization happens at different times or in different manner. And we make these synthetic observations and we compare them to the actual observations, and we use that to try to favor one model or the other, or even rule out one model. If we can rule out a model, that tells us a lot. So we do things like we look at the forest and we calculate certain statistics of the transmission of the forest. For example, how much small scale features are in the forest versus large scale features. How fine grained is the forest? There are statistics that quantify that. We compare it against those same statistics in our simulations. And if it's incompatible with that simulation, then we're able to rule that simulation out at some statistical significance. So that's kind of in a nutshell how we approach that particular topic.
Thank you. Okay, we do have a few more minutes for any extra questions that anybody would like to ask. And you did touch on how we can measure all the age of the what we observe. And am I correct in my understanding that the main way is the redshift, and the most accurate and then the most telling is redshift, and not much the other methods?
Yeah, well, if you're talking about galaxies, for example, you could look at the the emission lines that are produced by the interstellar medium of those galaxies, and you can see that they're redshifted, they're shifted over, and that tells you what epoch you're observing. It tells you but it doesn't tell you necessarily about how old the galaxy was at that time. And for that, you have to you actually fit models. So you run these models of the stellar populations of those galaxies, and different models produce different spectra. You know, different parameters produce different spectra. You fit the spectrum to those models, and that tells you about the age of the stellar population of that galaxy. So you have two senses in which you can speak of age: the age of the universe when that galaxy existed, when it emitted that light that you're looking at, and the age of the galaxy at that time. And you can get at these things all from the spectrum of the galaxy.
Thank you. And we have another question. It is generally accepted in the scientific community that large galaxies have a supermassive black hole at their center. Is this consistent with the observations of very early large galaxies?
It is. It's not ruled out by it. The thing is that it's possible to harbor a supermassive. It's a hard question because it's possible to harbor a supermassive black hole that's not shining. When it's in the shining phase, when it's vigorously accreting gas, that's called a quasar phase of a black hole. And as you go further back in time, the number of those quasars gets smaller and smaller. In fact, the number of supermassive black holes in general is much smaller. And so yeah, you know, the situation is we look at these galaxies as we go back to higher redshifts. There are no quasars in them. There's no evidence for what we call an active galactic nuclei necessarily that we have. But that wouldn't necessarily be inconsistent with this idea that every present day galaxy has a supermassive black hole sitting at its center. The black holes could be that we think the black holes are there. They're just in the process of growing, or they're maybe dormant, or maybe we don't understand exactly how they grow, because the black holes could be growing surrounded by dust, and that would obscure the light being produced from its accretion. And maybe it's because they're obscured that we don't see a lot of them at high redshift. So there's a lot that we don't know, but there, you know, yeah. So the observations are not in tension with that.
Thank you. And we have a question from the earlier in your talk. Do you believe there was an inflationary expansion that caused the CMB to be thermally connected?
Yeah, you know, I think you can ask almost any cosmologist, and they will tell you at the very least something like inflation had to happen. And one of the reasons is exactly what you cite, which is the fact that, you know, how could a patch of the CMB over there have actually to a high precision, the same temperature as a patch over there, or those patches are not causally connected with one another. They were never causally connected with one another. Well, at least without inflation. But what inflation does is that it provides a physical mechanism for actually connecting those regions. So those regions were in equilibrium at one point, and they were quickly inflated outwards outside of their horizon. So, and there are actually a number of other reasons, a number of other pieces of evidence in favor of something like inflation happening. We don't understand the physics of inflation. We don't understand what caused inflation. In fact, inflation turns out to be a rather robust consequence of lots of different types of models of physics. So yeah, the status is that something like inflation had to have happened in order to explain the observations of the universe. It's just a matter of understanding the physics of that.
And do we have any explanation for the imbalance between matter and antimatter in the early universe?
Yeah, I mean, so there are candidates. We don't know for certain what caused that, and that's an important, outstanding question in high energy physics, is to understand that asymmetry. But we don't know yet.
Thank you. Okay, I believe this is all the questions. And somebody has commented on my beard and how it is difficult to shave in space. Yes, it's very difficult to shave in space.
Imagine all the hairs would go everywhere. You have to have a vacuum.
I have to have a vacuum cleaner, yes.
Yeah.
Okay, so I believe with this, let me just, I'm reading here. Excellent. So we have all good feedback here. Okay, excellent. So apparently there are no other more questions. So I have a final few remarks I would like to make. Again, thank you very much, Dr. Daluasio. We have all hail for
Thank you
you.
very much for inviting me. I hope to be able to see you in person someday and attend one of your meetings. And
Sure, we do too. Okay, let me have my remarks here. I shouldn't have closed it. Okay, excellent. At the end, I would like to remind you of our next events in the reverse chronological order. We are going to have our next general meeting as usual on the second Friday of August on 14th at 7:30 p.m. in the same place as today. Dr. Jay Pasashov from Williams College will be talking about solar eclipses, math, science, and a spectacle. The other event we have is the Open Spiral Bar tomorrow, Saturday, July 11th, and at 10 p.m. It's an opportunity for all members to chat and socialize. And also, we have prepared a questionnaire to help us improve the quality of our meetings and would appreciate everybody's participation. This questionnaire should be already open in your browser, so please do fill that out and help us out. With this, I wish everybody a very pleasant rest of the night and hope to see you again tomorrow night and thereafter. So everybody, have a bye.